Welcome to the first fundamental theorem of calculus. There are actually two parts to the fundamental theorem of calculus, and this is the first one. Different textbooks talk about the fundamental theorem of calculus parts 1 and 2 in different orders, and so I am just going with our textbook and how I learned it. So the first fundamental theorem of calculus for us may be what other students learn as the second. It doesn't really matter so long as we know that there's two parts to the fundamental theorem of calculus. Before we begin, we do just need to make sure that we understand some of the difference with the verbiage that we've been using. We have two different types of integration, indefinite and definite. The difference is with indefinite integration, there are no limits, the lower limit and the upper limit, for the integration. So we do not have values here and here. With definite integration, we do. We have an a and a b value here. This is how we first learned how to take the antiderivative or evaluate an indefinite integral. Those mean the same thing. Basically, here are the ways we can tell if something's an indefinite integral. Like we just said, there are no limits of integration. The answer that we get out of this is a general solution, and we have to put plus c at the end to account for the possibility that there was a constant in our antiderivative. Of course, we learned that if we are given some initial condition, an x and a y, we can find that specific plus c. However, it still makes it an indefinite integral. So with indefinite integrals, we do not have numerical values here, and the output that we get is a function. It's a general solution, and it needs a plus c. With definite integration, we saw that definite integration represented the area underneath the curve down to the x-axis. Yes, this could also be a negative value if it is below the x-axis down to the curve, but the main idea with definite integration is that we do in fact have numerical values here called the limits of integration. We do not get a general solution out, instead we got a numerical value out. We did not need a plus c. Now so far, we have evaluated definite integrals by sketching the area underneath the curve and using this long and tedious limit process as n goes to infinity of the summation from I equals 1 to n of f of c sub I times delta x. We did all of that, and that is the long way to find the value or the numerical value to a definite integral. The first fundamental theorem of calculus provides us with a shortcut of sorts to not have to do that long limit process to find the area underneath a curve anymore. We can use the first fundamental theorem of calculus, and that tells us a surefire, much easier way to evaluate a definite integral. Here is the first fundamental theorem of calculus. We have if a function f is continuous on the closed interval from a to b, and capital F is its antiderivative, then here is the simple way to find the numerical value of the integral from a to b of f of x dx. What we do is we find the antiderivative of little f, which is defined as capital F. We then evaluate that antiderivative at the upper limit, evaluate it then at the lower limit, a, and then subtract. Let's take a look at an example to see actually how simple this truly is. We have our little function here, f of x, as x cubed. In order to find capital F, we have to take the antiderivative of x cubed. So I'm going to use the power rule for integration. To do that, I add 1 to my exponent and I divide by that out in front. So we can write it as x to the 4th over 4 or simply as 1/4 x to the 4th. I don't need to put a plus c because this is a definite integral and we are going to evaluate it at these two values here and then subtract to get a final numerical answer. So no plus c because we have a definite integral. Now I can check my work right here and quickly take the derivative to make sure I get x cubed. 4 times 1/4 is 1, 1 less than 4 is 3, so we end up with x cubed. Perfect. Then what I'm going to do is actually evaluate this at b and at a in my next line. Now the way that we can write this, and we'll learn this shortly, to sort of some calculus notation, in order to evaluate it at 3 and then subtract at 1, we can write it just like this. So what I'm going to do now, I note that b is my upper limit, it's 3, a is my lower limit, it's 1, and this function right here, 1/4 x to the 4th, is capital F, or capital F of x. So I first need to evaluate it at 3, which means plugging in 3, to our function here. So I've first done f of b because b is 3. So I have 1/4 times 3 to the 4th. Then I'm going to subtract and evaluate this function here, 1/4 x to the 4th, at a, our lower limit of integration, which is 1. So now we have 1/4 times 3 to the 4th. 3 to the 4th is 81. So we'll have 81/4. 1 to the 4th is just 1 minus 1/4. So this gives us 80/4, which is 20. So that was a lot easier to evaluate than doing that tedious limit process as n goes to infinity. I sort of liken this to at the beginning when we learned how to take the derivative of a function at a certain point, and we had to take the limit as h approached 0 of f of x plus h minus f of x all over h, and then we learned the derivative rules, which was kind of a shortcut. This is along those same lines. Now, what does this mean? Let's sketch it out real quick. So we'll need some room. We have our function f of x equals x cubed, and we want to find the area underneath that curve, x cubed, down to the x-axis between x equals 1 and x equals 3. Well, x cubed, if we plug in 0, we'd get 0. If we plugged in 1, we'd get 1 out. But if we plugged in 3, we'd get out 27. So we're going to have to go up pretty high here. So I'm going to go by 5s. So here's a quick sketch of cubic function, the parent cubic function, f of x equals x cubed. Looks something like this. 20 represents the area. I'll do that in yellow. 20 represents the area under that curve from 1 to 3, right here. So this entire area down to the x-axis underneath the curve f of x equals x cubed, we know is represented by the definite integral from 1 to 3 of our function x cubed dx, and we have just found that that equals 20 square units because it is area. And we found that quickly using the first fundamental theorem of calculus, which allows us to evaluate a definite integral without using the long, tedious limit process. Here are a couple guidelines for using this first fundamental theorem of calculus. So number 1 we've already addressed. If you can find an antiderivative of f, then we have a way to evaluate a definite integral and get that numerical answer without having to use that long, tedious limit process to find the limit of a sum. When we're applying the fundamental theorem of calculus, we talked about using this notation. We find the antiderivative, then we put these sort of brackets here around it to show that we're about to evaluate it at b, and then subtract evaluating it at a. That's what this means here. This was the example we just did, writing it out. It is not necessary to include that plus c using these definite integrals, and here is a mathematical explanation as to why. If we did include that plus c, and we're evaluating it with the plus c at b and then subtracting at a, we would have f of b plus c, but then we're subtracting f of a plus c. We'd essentially have a plus c minus that same c. So the plus and the minus c's end up canceling out, which is why with definite integrals, when we're evaluating to find a numerical answer, we do not need to use a plus c. Let's evaluate 3 definite integrals using this first fundamental theorem of calculus. We will also explore why certain answers are negative while others are positive by looking at them visually. In part A, we want to find the value of the definite integral from 1 to 2 of x squared minus 3 dx. Now I have sketched x squared minus 3. It is simply the parent parabola x squared shifted down 3 units, so its vertex is at 0, -3. And we want to find the area either under or above the curve, up or like down to the x-axis, depending on, because if we take a look between 1 and 2, here and here, we can see that our function is both under and above the x-axis. So if we look at it as 2 separate parts, from this value right here is the square root of 3. So if we go from 1 to this value here, the square root of 3, we can see that our function is under the x-axis, and therefore the value of this integral, definite integral right here, would actually be negative because it's beneath the x-axis. Whereas if we looked from root 3 to 2, again splitting this into 2 parts, this would be a positive section right here. Now the positive section is much smaller. So if we look here, this positive section in yellow the area of that is less than the area of our negative section, which I'll do in blue, underneath. So the negative area, I don't really like using the term negative area, but area is technically always positive, but since it's underneath the x-axis, it is going to have a negative value. We can see that the area that will have the negative value sort of wins out over this area that will have the positive value. And that's because this area is greater than this area. But we have to add them together in order to get our final answer here from 1 to 2. Well, that means that our final answer here is going to be negative, because this negative value right here has a greater magnitude or absolute value than this positive value up here. So the negative is essentially going to win out. Now, did you have to know that before evaluating this? Absolutely not. You could simply use the first fundamental theorem of calculus to evaluate, but you would get a negative answer. So I just wanted to show why that is. Let's evaluate part A. So what we want to do is take the antiderivative of what's inside here. So we're going to use the power rule for integration. We'll end up having 1/3 x cubed, and then the antiderivative of minus 3 is minus 3x. Again, we don't need a plus c because we're taking a definite integral. If you wanted to quickly take the derivative of these two terms, you would see that you would get back to here, the integrand. Then we're going to evaluate this, put parentheses around it to show the whole thing, at 2 and subtract its evaluating at 1. So we will first evaluate this at 2. We'll have 1/3 times 2 cubed minus 3 times 2. That's evaluating it at 2. So that's a whole piece here. Then we're going to subtract and evaluate it down at 1. So when we evaluate this at 1, we'll have 1/3 times 1 cubed minus 3 times 1. Getting both of these, this gives us 8/3 minus 6. And in our second parentheses over here, we'll have 1/3 minus 3. Now it is important to be careful with all this algebra here to keep things sort of either in brackets or parentheses, whatever you prefer. I use the brackets around these big parts here, f of b minus f of a in each one, because I already had small parentheses inside each one, but it's completely up to you. 8/3 minus 6 is 8/3 minus 18/3, so we'll end up getting negative 10/3. Over here inside that next parentheses, we'll have 1/3 minus 9/3. So we're subtracting minus 8/3. Minus a negative becomes one giant plus. So our final answer ends up being negative 2/3, which is approximately negative 0.67. So our answer is negative again because of the explanation given previously. In part B, we want to use the same process here and use the first fundamental theorem of calculus in order to evaluate this definite integral. So I'm going to rewrite this definite integral as 3x to the 1/2 dx. I've not done any calculus yet. I've simply rewritten using algebra. Now I'm going to use the first fundamental theorem of calculus and take the antiderivative of the integrand here, what's inside the integral. 3x to the 1/2 looks like in order to take the integral, or to antiderive it, we can use the power rule for integration once more. So I'm going to add 1 to our exponent of 1/2, which is 3/2. So we'll have 3x to the 3/2, and then I need to divide by 3/2 as well. Well, dividing by 3/2 really means multiplying by 2/3. So I'm really multiplying by 2/3 out in front. The 3's cancel, so we're left with 2x to the 3/2, and we want to evaluate that at 4 and 1. So we will first evaluate this at 4. So evaluating this at 4 will be 2, and then we're taking 4 and raising it to the 3/2 power. Then we want to subtract and evaluate at 1, our lower limit of integration, and do the same thing. So we'll have 2 times 1 to the 3/2 power. We have to remember from the very beginning of the year when we sort of learned some algebra hacks here, 4 to the 3/2 or anything to the 3/2 means taking the square root and then in this case cubing it. So we're doing two different things. So we have 2 and then we're taking the square root of 4 and then cubing it. So that's really what this means here. It means the same thing for 1, but 1 to any power is just 1, so we don't need to go through all that rigmarole. We'll just have 2 times 1, which is just 2. All right, the square root of 4 here is 2. 2 cubed is 8. So we really have 2 times 8 as our first term. And so our final answer ends up being 14. Here is the curve f of x equals 3 root x. It is, of course, the square root of x parent function multiplied by 3, so it's like a little taller. So the square root function is just like an arc, and multiplied by 3, our outputs, instead of being 1, 1, it's 1, 3, and instead of being 4, 2, it's 4, 6. So we can see that the area underneath this curve from 1 to 4 is a pretty big chunk. It's not the greatest line there, but that's okay. It's this entire area here. It's down to the x-axis. It's completely all positive because it's above the x-axis, and it's a pretty large area. It is 14. We could not necessarily do that without, maybe we could, using some sort of circular function, but it's much easier to use calculus here because this is not a geometric shape we can necessarily take the area of, but the first fundamental theorem of calculus tells us that the area underneath this curve down to the x-axis is 14. In part C, we want to find the definite integral from 0 to pi over 4 of secant squared dx. The antiderivative of secant squared is tangent, and using the first fundamental theorem of calculus, we want to evaluate this tangent of x at pi over 4, then subtract it being evaluated at 0. The tangent of pi over 4, that's easy enough to plug in, minus the tangent of 0. At pi over 4, our tangent is the y-coordinate divided by the x-coordinate. They're both root 2 over 2 if you take a look at your unit circle, and therefore the tangent at pi over 4 is 1. At 0, the y-coordinate is 0 and the x-coordinate is 1. Therefore, when we do 0 over 1, we'll get 0. So the tangent at 0 is 0. Subtracting, the answer to this definite integral here is 1. Since the secant squared function is kind of weird, I graphed it on Desmos just to explore it a bit. And from 0 to pi over 4, well, we know where 0 is, but pi over 4 using a calculator is about 0.785, so almost 0.8. So if we take a look here, pi over 4 is at about almost 0.8, therefore it's somewhere in here. So that means the area between 0 and there is, under this curve here down to the x-axis here, 1 square unit. A common function that we see often in calculus is the absolute value function, or some sort of absolute value function, as in this example down here. A quick recap of the definition of the absolute value function is as follows. Whatever is inside the absolute value, in this case x, is exactly that, positive, for when x is greater than or equal to 0, when x is positive, or it's defined as the opposite of what's inside the absolute value when x is less than 0. Let's see why this is graphically. This is our absolute value function, color-coded for each side. The absolute value function always forms a v. And so we can clearly see that this line is just the positive line y equals x to the right of the y-axis, and it is the line y equals negative x to the left of the y-axis. That is the reason that the absolute value function is defined as a piecewise function. Let's take a look at this function down here. We know that according to the definition for absolute value, this function equals exactly what's inside for x is greater than or equal to some number, and we know that it equals the opposite of what's inside. So actually, I'll do that off to the side real quick. If we take negative what's inside, it simplifies to negative 2x plus 1. So I just wanted to write that in a more simplified way, distributing that negative. For x is less than that same value. Now, how do we find out what that value is? We basically want to know when this equals 0 to know what's inside here, when it equals 0 to know when it was something positive versus when it was something negative. So let's set this equal to 0 real quick. And when we solve, we'll see that the vertex of this function, when it hits the x-axis, is going to be at 1/2. So we have, it's this piece versus here for the piecewise function. Let's see how this looks. So we have the line 2x minus 1, but only where x is greater than or equal to 1/2. So I'm just going to plot the line 2x minus 1. So I'll go up 2 over 1, up 2 over 1, and so on. But I only want this when x is greater than or equal to 1/2, which is right here. Then I want the line negative 2x plus 1 when x is less than that point here. So we'll start at positive 1 and go up to left 1 to get that slope of negative 2, and we can see that they intersect right there at the vertex. Now, could we have also plotted this on our graphing calculator or on Desmos and not needed to do this whole thing? Sure. I just wanted to sort of review how we can graph absolute value. So we actually want to evaluate the definite integral from 0 to 2. We can see that this is, in fact, two small triangles, this one right here, between 0 and 1/2, and then the rest of the way would be from 1/2 to 2, which is this triangle. So we could do this kind of with just using geometry like we've done previously, but let's explore how we can do this using the fundamental theorem of calculus. So we can see that this first small triangle from 0 to 1/2 is actually using the green function, where going from x equals 1/2 to 2 is using the yellow part. So we have that this original guy right here equals the integral from 0 to 1/2 of the left side of the v, which is negative 2x plus 1 dx. Then we need to add the remaining part, which is plus the integral from 1/2 to 2 of 2x minus 1 dx. Now, we did need to know how to split it up like this because we cannot take the antiderivative of this piece originally with the absolute value. We had to understand that absolute value is two separate linear functions and where they split. Now, we could have found that kind of without using this, and if we just graphed it on Desmos or our graphing calculator, but we still had to get that graph in order to understand this piece right here and splitting it up into two separate integrals. Now we can use the fundamental theorem of calculus to evaluate each one. Doing the green integral first, we will use the power rule for integration. So we'll have negative 2x squared, but then dividing by 2. So that'll just give us negative x squared. Then the antiderivative for plus 1 is just plus x. We're going to evaluate that at 1/2 and 0. Then I'm going to add on our 1 in yellow. This is a very similar antiderivative in that it's just x squared minus x, and we're going to evaluate that one at 2 and 1/2. Plugging in here, we'll have negative and then times 1/2 squared plus 1/2. Then the interesting thing here is that we have a 0. Now we can clearly see that if we evaluated this here at 0, we would just get 0. Therefore, I'm not going to even bother evaluating at 0 and subtracting it, as it's not going to change the overall output. I can move directly on to evaluating what's in yellow. So the first thing we want to plug in is 2. So we'll have 2 squared minus 2. And then we want to subtract, evaluating at 1/2. So when we evaluate at 1/2, we'll have 1/2 squared minus 1/2. A lot of parentheses here. You can choose to kind of do as many parentheses as you want, but this is just kind of what helps me. All right, let's focus on what's in green first. Squaring 1/2 gives us 1/4. So we have negative 1/4 here plus 1/2, and that gives us a positive 1/4 output for what's in green. Next, I'm going to simplify what's in here. So this is 4 minus 2. So that first parenthesis is just a 2. Minus the next one here, what's inside here? So we will have 1/2 squared, which is 1/4, minus 1/2, so that'll be a negative 1/4. So I essentially have 2 plus 1/4, which would be 9/4. Of course, we can see what our final answer is, but let's take a look back at the visual representation of this. We can see that looking at the visual representation, the area of this tiny piece under the curve from 0 to 1/2, that was only 1/4 of a square unit. And then the area of this part from 1/2 to 2 under our curve was 9/4. So we could have gotten that either from geometry or using the first fundamental theorem of calculus. Adding them together gives us the total value of the definite integral underneath the curve, which is 5/2, or 2.5. So visually we can see what this means. It is the two areas added together. We could have used geometry, or we could have used the first fundamental theorem of calculus, which is what we just did. In this video, we explored the first fundamental theorem of calculus, which gave us a much simpler way to evaluate definite integrals.